Okay, ladies and gentlemen, let's continue with chapter 6 on convection heat transfer. The chapter is about the fundamentals of convection, and it is a very, very important chapter because it is the groundwork for the 3 chapters following after chapter 6. And those chapters will be convection, external convection, internal convection, and natural convection. It's quite a long chapter. There are lots of fluid mechanics in it, lots of work that you should be familiar with, but it is very important that you revise it again because it is so part of the fluid mechanics are so integrated into the heat transfer that you really need to understand it very well and you need to be able to use it. Okay, so with the previous lecture we've looked at paragraph 6.1, the physical mechanism of convection, and then there was a paragraph 6.2 on the classifications on fluid flow, which I didn't do in detail because you should be familiar with it, so please go and read it again. It is about viscous versus inviscid regions of flow, internal versus external flow, compressible versus incompressible flow, laminar versus turbulent flow, natural or unforced versus forced flow, steady versus unsteady flow, and 1, 2, and 3-dimensional flows. The only thing that I've revised just quickly is the difference between compressible flow, incompressible flow, and steady and unsteady, and usually the combinations that you might have with compressibility, which confuses students a lot. So let's continue with paragraph 6.3. It's a little bit of a revision of what you've done in fluid mechanics, but there's critical parts that I'm going to take out of it, and I'm going to show you later on how it fits into the heat transfer. Okay, so let's just look at it very quickly. And we look at the velocity boundary layer, and I hope you can remember if you've got a flat plate and you've got a uniform flow velocity flowing over that flat plate at a velocity v, then there are different regimes that's going to follow or develop onto the flat plate. And in general, they can be divided into 3 parts. Okay. A laminar part, a part of transition, and a turbulent part. Okay, so the first part is laminar, then that one is turbulent, and this one is transition. Okay. Now, this distance is called the critical distance. So that is the distance, how long it takes before the flow changes from laminar flow into a transition or turbulent flow. What I'm going to do is I'm going to specifically concentrate on the velocity distribution in the laminar flow regime and in the turbulent flow regime. We're going to ignore this one as it is historically been ignored in fluid mechanics and typically also in pipe flow, and lots of literature would actually tell you to stay out of it because it is a very unpredictable region, and there are lots of changes, lots of pressure fluctuations, and for that reason stay out of it. In our laboratory at the university, we actually did a lot of work in the transitional flow regime, not on flat plates but in pipes, and we've actually found that it is very, very highly predictable. But that is another subject. So just take note of it. So what I'm going to do is I'm specifically going to look at what happens in this flow regime A and in that one B. Okay, in the laminar and in the turbulent flow regimes. Okay, so let's look in the regime A or in the laminar flow regime, what happens with the velocity distribution. Now typically if you would go and measure the velocity distribution in the laminar flow regime, the velocity distribution is going to look like that. So what does it mean? It means if you've got a very sensitive instrument and you could measure it, without disturbing the flow, which is quite a challenge, then far from the plate, you're going to measure the free stream velocity v. Okay, and as you come closer and closer, things would start changing. Okay, up to a point where that velocity is equal to 0.99 v, which is 99%. Okay, so it means there's a 1% change in velocity. Okay, now the moment we get there, then that distance is known as the boundary layer thickness, delta. Okay, and this gradient here is very, very important because it is equal to partial du dy, where y is equal to 0, and that would then be if we would choose our axis xy to start from the flat plate. Okay, so that is equal to partial du dy. It's the velocity gradient at that point there, and we also know at that point there the velocity v or u or whatever you want to call it is equal to 0. There's a no-slip boundary condition on the wall. Okay, now the wall shear stress is an important thing for us. Why is it an important thing for us? Because that's the drag. Okay, and in many cases we are very interested in what is a drag.
Do you have a projector, maybe, by any chance?
Projectors are up there. They are not. No, not a. Okay, okay. Okay, wall shear stress. Okay, so the wall shear stress is important because of drag, and that is equal to the viscosity multiplied partial du dy, where y is equal to 0. So this term is that gradient, okay, the velocity gradient on the wall. And we know that the viscosity is μ, and we call this one the dynamic viscosity. Okay, the dynamic viscosity, as you know, there are two of them, and they're going to appear a lot in this course, and that is why I just want to highlight them again. So it's the dynamic viscosity with units of kilograms per meter second. Okay. And then we have the kinematic one. The kinematic one, which by definition is equal to the dynamic viscosity divided by the density, and its units would then be meters squared per second. Okay. Just a little bit of a revision. Right. Now the viscosities is interesting. We know that there are two different types of relationships here. We have relationships where there's a linear relationship of the viscosity, which are called Newtonian fluids, and water and air and most of the fluids that we as engineers work with, fortunately, are Newtonian fluids. There are exceptions, for example, blood and liquid plastics. They do not have this relationship, so then it would be more complex. But in general, if we look at typically how the viscosity behaves as a function of temperature, then for liquids there will be a decrease in viscosity, and for gases there's in general an increase in viscosity as a function of temperature. Okay. Just so that you can get an idea of the orders of magnitude, let's look at typically the viscosity, which would then have the units of kilograms per meter second of air and oil. Air and water. Let's take air and water. And we're going to do it at temperatures of 0, 20, 50, and 100 degrees Celsius. Okay, air and water. Specifically now in terms of what I've shown you here, how does it change as a function of temperature? So air typically at 0 degrees Celsius is equal to 1.73, everything multiplied by 10 to the minus 5. Okay, so I do not want to add the minus 10 to the 5 for each term now. Okay. So 1.73, then it is equal to 1.8, 1.9, and 2.2. Okay. And for water, it's typically 1.8, and it would now be every term multiplied by 10 to the minus 3. Everything multiplied by 10 to the minus 3. Right, so for water, 1.8, there it's about 1, 0.5, and about 0.3. Okay. So air is a gas, and we can see it increases the viscosity, while with a liquid, the viscosity decreases. It's a function of temperature. However, and that is very important, in many cases we are going to make the assumptions that something like the viscosity is a constant, the thermal conductivity, and the Cp, etc. So the question would now be, but how can you assume that? Obviously you can see it is a function of temperature. The answer is, it's not a strong function of temperature. This is a huge scale. If we look at typical temperatures where heat transfer occurs, a heat exchanger typically, delta T's of about 10 degrees. Okay. So normally the delta T's, temperature differences that we work with in heat transfer, are very seldomly in hundreds, maybe orders of tens, and therefore, if you look at those delta T's, you will actually see that the changes typically in viscosities, in most cases or for many practical problems, are actually for all practical purposes constant. Okay, right. So that was now the velocity distribution in the laminar flow regime. Let's look at it in regime B, the turbulent flow regime. How does it look there? The turbulent flow regime, again, if we start taking measurements far away from the wall, come closer and closer and closer, and again it is with one of those magic instruments that we haven't developed yet, where we can go and measure without disturbing the flow, then the velocity distribution would typically look like this. Okay. It looks different, and typically like that. Okay. Again, that would be the velocity v. Okay. And if you start going downwards, and again that is equal to 0.99 v, then that would be the boundary layer thickness. Okay, the boundary layer thickness, 99% of the free stream boundary. Again, this gradient is very, very important to us because it is equal to partial du dy, where y is equal to 0, and it gives the shear stress on the surface, which is going to be the drag, or it is going to be the pressure drop in a pipe, okay, that we pay for with a pump. Okay. And typically, in terms of these types of characteristics, I've measured a pipe, I've mentioned a pipe just now. If I can just go back to the Moody diagram, the friction factor as a function of Reynolds number, there's a direct relationship between the friction factor and tau, or the friction coefficient. I'm not going to do the derivation of that, but just to give you an idea, then if you look on the Moody chart, you'll see that it looks typically like that. And then for a smooth tube, epsilon divided by d is equal to 0. Then you'll have a line like that. And for different surfaces, different roughnesses, then typically that would be the response or the results. So this is in the laminar flow regime. Okay, remember, that is laminar and that is turbulent. And this is transition. So if you look in your Moody chart at the end of your textbook, you will see a gray area like that. Why? Because they say, well, stay out of it. It's not a good idea to design in this flow regime, but actually all the measurements these days shows that it typically looks like that, okay, for a smooth tube, and obviously for a rough tube it would be something like that. So it is very, very highly predictable, and most probably it is time that this Moody chart should be revised and updated. Okay. Now the important thing here is all good and well to see this friction factor as a function of Reynolds number and the changes that happen here in the transition flow regime. It might be interesting or not. The reality is, what does it really mean? What does it really mean? It means that, okay, the moment that that happens, okay, what happens there? Obviously, we can see the friction factor increases, but what does it really mean for your pocket as an engineer or for your client? It means an order of magnitude increase in friction factor or an order of magnitude increase in pressure drop. Okay. So there's an order of magnitude increase, okay, in friction factor or pressure drop or whatever you want to call it, or an order of magnitude increase in drag. So on a flat plate, there are similarities with a tube. If you look at that wall shear stress as a function of x, then it actually looks something like that. Okay. The reasons we are not going to discuss now. It has been done in fluid mechanics, and as you can see, that is what is going to happen on a flat plate. So what we can also see is that the shear stress is a function of x. Okay, and does it make sense? I mean, if we look at this velocity gradient that changes, means the shear stress should change. It goes through the transition flow regime and here in the turbulent flow regime again. So the shear stress changes as you go downstream the plate. As engineers, obviously, we in most cases interested in the average. Okay, if we've got the average shear stress or the average drag, then we can design something and do something with it. Okay, where does this transition occur? For a pipe, where does the transition occur at a Reynolds number of? About 2,300, okay. And for a flat plate? For a flat plate? It's not 2,300 or 2,100, okay. Remember that the Reynolds number is always based on a characteristic length. So for a tube or a pipe, it would be the diameter. Okay, so we would rather put a D there to indicate it is the Reynolds number based on the diameter. If we have a flat plate or an aerofoil or the Airbus wing, there's no diameter. So the question is now, what do you choose now in the selection of the characteristic length? Usually the chord of the aeroplane wing. Okay. So in this case, it would be approximately 300,000 to 600,000. So for a flat plate, the transition is not the same as for a tube. So this value of 2,300 is only valid for tubes. It is not valid for your car. It's not valid for an Airbus. And it's not valid for your own body if you run in air or in water. Okay, so it depends on the geometry. Okay, now let's just go back to the shear stress. The shear stress, which is equal to the viscosity multiplied by partial du dy, where y is equal to 0. Okay. That means, again, if we want the shear stress, we need to know the velocity distribution inside here. Okay, so we need to get inside it the gradients to get the shear stress, okay, as it changes downstream of the plate. Okay. So what do we as engineers do? Well, what we do is we say, well, let's go and do some experiments in the lab, and we measure the average, okay, and then we write it as equal to CF multiplied by rho V squared divided by 2, where that is equal to the friction coefficient. Okay, the friction coefficient or the skin friction coefficient. Friction coefficient or the skin friction coefficient, and we would therefore go and determine it experimentally. Okay, that is just a little bit of a revision on the velocity boundary layer. Now we have to do the thermal boundary layer. Okay, paragraph 6.4. Okay, thermal boundary layer. The thermal boundary layer, again, we have a flat plate. And now, if we would go and measure in the flow field, okay, so this is the flow field V, and these distances are not vectors. They will be an indication of the value of the temperature. Okay. So let's suppose this is 100 millimeters for 100 degrees Celsius. Okay. So if you would measure everywhere in the flow field, and you measure everywhere 100 degrees Celsius, then that is typically how the flow field is going to look like. Right. Now in that boundary layer, we have the same type of behavior. We've got the thermal boundary layer, or how the velocities or the temperatures changes in the laminar flow regime, the transition and the turbulent. And guess what? It is very similar to what happens with the velocity. So the profiles look the same. Okay. There's just one difference. Okay. And that one difference is that if we would now typically let me do it here. If we would typically now look at those measurements there, then they would typically look like that. Okay. Then they would decrease here close to the wall. However, it wouldn't go to zero. Okay. It wouldn't go to zero, depending on what scale you're using. Okay. So let's suppose that was 100. Okay, 100. And the surface is at 20 degrees Celsius. Okay. Then that temperature or that scale here is going to be 20 millimeters. Okay, so if I would draw it to scale and the temperature on the plate is 20 millimeters, then that is that length, that is 100 degrees Celsius, and that is now how the temperature profile is going to look in the boundary layer. Okay. So now, if we want to use the same concept of the boundary layer thickness than with the velocity boundary layer, we cannot really say it is equal to 99% of that, okay? Because we have this value of 20 here. So if the plate was at 0 degrees Celsius, then it would work. Okay. So what we would do is we would say that the boundary layer thickness, if I can take this out here, the boundary layer thickness, if I can draw it like that, this one is now called the thermal boundary layer thickness. Okay, and the thermal boundary layer thickness is equal to 0.99 times multiplied by T infinite minus Ts. Okay, so it is it's 99% of the difference between the two. Okay, so that is called the thermal boundary layer. thermal BL is boundary layer, a thermal boundary layer. The previous one was called a velocity boundary layer. Right, in terms of what we've derived in the previous lecture, we've derived that the heat transfer coefficient is equal to minus K of the fluid multiplied by partial dt dy, where y is equal to 0 divided by Ts minus T infinite. So guess what? Okay, guess what? If we look at this term here, it is equal to that gradient there, partial dt dy, the thermal gradient in the thermal boundary layer. Okay, so what it says is that the heat transfer coefficient is directly proportional to, obviously, K of the fluid and the temperature gradient. Okay. The similarities, do you see the similarities? With the drag, okay, with the drag, the fluid mechanics, the drag is proportional to the velocity gradient. Okay. In heat transfer, the heat transfer or the heat transfer coefficient is proportional to the thermal boundary layer. Okay. Right. Let's introduce a new number, and that is called the Prandtl number. Okay. Now, Prandtl was a brilliant fluid mechanics guy. He did his work in the 1800s, the 19th century. Okay, and the Prandtl number is named after him and is defined as, okay, the molecular diffusion of momentum. The molecular diffusion of momentum divided by the molecular diffusion of heat. Okay, the Prandtl number is the definition. Definition is it is the molecular diffusion of momentum divided by the molecular diffusion of heat. Okay, so just like the Reynolds number, which is the ratio of viscous forces to inertial forces, the Prandtl number is the ratio of how fast heat would transfer because of these two things, momentum and heat, in the ratio of the two. Okay. And what it actually says is that it has to do with the boundary layer thickness divided by the thermal boundary layer thickness. That is what it means in essence. Okay. The ratio of the two is the Prandtl number. Very important number. Okay. And let's consider three possible scenarios. Okay. Okay. And that would be the scenarios on the flat plate. Okay. And if you have a blue pen and a red pen, then please use them. Okay. And what we're going to look at now is the different possibilities of the boundary layers. Okay. We have looked at the boundary layer, which is delta, and the thermal boundary layer. Now it can be that the one is thicker than the other because of the Prandtl number. Okay. So there are three possible scenarios approximately. Okay, now the first scenario is where that is the velocity boundary layer. I hope you can see the blue. Okay, so that is the velocity boundary layer, and that would be equal to delta. Okay, the velocity boundary layer. Okay. Then that would be the thermal boundary layer in red. Okay, the one with the heat. It indicates the heat, the thermal boundary layer. Okay, and that distance would be delta T, the thermal boundary layer one. Okay. What would what would be the result of a boundary layer like that? The result would be, firstly, that in this case, the Prandtl number would be smaller than 1. Okay? It means heat diffuses slowly and typically we would get this type of behavior when we use liquid metals. Okay. And why would we use liquid metals in heat transfer? Well, it is being used in nuclear reactors, for example, where there's small surface areas and lots of heat that needs to be transferred. Okay. So the heat diffuses slowly, liquid metals, and the problem, however, with liquid metals is it's very corrosive. So that is why we do not normally want to use them, except in very, very specialized cases. Okay. So that is the one possibility. Now the second possibility is that if this is the thermal boundary layer or the velocity boundary layer, then the velocity boundary layer and the thermal boundary layer would be approximately the same. Okay. And that would mean it is the case of Prandtl numbers approximately equal to 1. Okay. So what I'm referring here to is approximately, although I've drawn them there on top of each other, they are in the same order of magnitude. Okay. The same order of magnitude. Okay. Now, this one is a very special category for us because many of the fluids that we work with actually falls into this category. For example, air, gases. All of them have Prandtl numbers of approximately 1. Okay, air is typically, depending on the temperature, 0.7 at about 20 degrees Celsius. So order of magnitude approximately 1. So these two lines will not lie on top of each other, but close to each other. Okay. Then the third possibility is now the opposite of that. That is where the thermal boundary layer is very thin in comparison with the velocity boundary layer. That one there, the velocity boundary layer. And if I can put in the deltas also, that is the one for the velocity boundary layer, and that one is for the thermal boundary layer. Okay. So for this one, Prandtl numbers is larger than 1. And now the heat diffuses quickly. The heat would diffuse very quickly, and oils would typically fall into this category. Just to give you an indication of different types of fluids and their Prandtl numbers. Different types of fluids and their Prandtl numbers. Okay, so liquid metals would typically have Prandtl numbers of about 0.03. Okay, and gases, specifically including air, approximately 1. Okay, water, about 10. Okay. Water at 20 degrees Celsius is about a Prandtl number of about 7. Okay. And then glycerine, oil, let's first do oil. Oil typically about 50 to 100,000. Okay. And then glycerine is about 2,000 to 100,000. Okay, very, very high values. Okay, while you finish up there, I just need to clean the board on the side. Okay, ladies and gentlemen, are you following? Okay, let's continue with paragraph 6.5, laminar and turbulent flow. You've done it. I just want to highlight one or two things which are very important. Paragraph 6.5, laminar and turbulent flow. Laminar and turbulent flow. Okay. Now when we think of laminar or turbulent flow, and to determine when it will be laminar and when it will be turbulent, we immediately need to think of the Reynolds number. Okay. So the Reynolds number is the ratio of inertia forces to viscous forces. The ratio of inertia forces to viscous forces, and it is equal to, you can write it as the velocity multiplied by the characteristic length divided by the kinematic viscosity. For most of you would immediately say, but does it really look very familiar to me? You can write it also as rho V multiplied by L divided by the viscosity. Okay, so that's the reason why I've just quickly revised the difference between the dynamic viscosity and the kinematic viscosity. Okay, so the Reynolds number is a very important criteria for us. Okay, now what is the most important difference between laminar and turbulent flow? Well, I'm going to show it to you like this. Let's suppose we have a flow field. Okay. A flow field, typically smoke may be in air, okay? Just look at smoke in air. Then you can see typically different laminates. Okay, the flow is in different layers and they sort of flow parallel to each other. Okay, and if we would then take a measurement in that flow field, okay, and we would measure the flow as a function of time, okay, with some of the best instruments available on the market, then the velocity as a function of t would do something like that. It would be a constant. Okay, there will be no changes as a function of time. That is laminar flow. Right. Now let's suppose we put on a fan behind it, and now you know the flow is going to do something like that, which is called turbulent flow. And if we now also take that same measurement, now the velocity most probably is going to be higher, okay? But now the average is going to be a constant, but if we have a very good instrument, we're going to measure something like that. We will measure lots of fluctuations, okay? So if we enlarge that, then typically we would have something like that. Okay. Now this velocity is called the average velocity. So the average is a constant. But if you would take measurements very, very accurately, you would see that there are fluctuations. Okay. So the result is that we would call that the velocity u that we want to measure is always equal to the average plus the fluctuations as a function of time. Okay. Okay, that is just some of the most important things I want to take out of the textbook. There's more, so please go and read it. Okay. Then it follows on to paragraph 6.6, which is heat and mass transfer in turbulent flow. Okay, heat and mass transfer in turbulent flow. Okay, for those of you who didn't follow it, heat and mass transfer in turbulent flow. Okay, I don't have time to write it all out. Okay, heat and mass transfer in turbulent flow. Okay. Now using this concept of looking at the fluctuations as a function of time, we can use exactly the same to measure the temperatures. And again, just like in the velocity boundary layer, nature tells us that things are very similar. So what people did is that they've actually, when they looked at heat transfer, they've used all the work that was done in fluid mechanics, and in many cases, or in most cases, there are lots of similarities. And some of the similarities that I would typically just like to show you is that typically for turbulent flow, for turbulent flow, the shear stress can be written as the viscosity plus, a turbulent component of it, multiplied by partial du dy is equal to rho multiplied by v plus vt multiplied by partial du dy. Okay. So these would be the average values, and these would be the fluctuations. Okay. Why do I want to show you that? Because I want to show you that if that is now used in heat transfer, then the heat flux in turbulent flow can then also be written as equal to minus K plus KT multiplied by partial dt dy is equal to rho multiplied by Cp multiplied by alpha plus alpha t multiplied by partial dt dy. Do you see the similarity? So that is the most important thing in that paragraph. Please go and read it, take note of it, it is quite important. And then we go on to paragraph 6.8, which is about the solutions of convection equations for a flat plate. Okay, the solutions for a flat plate. Okay, now just think back of 200-300 years when people started studying fluid mechanics, okay? And we've already seen how complicated it is in terms of all the equations. Now, what is the best approach if things are very, very complicated? Well, you would not really go and try to understand the flow around the wing of an Airbus with flaps out. It's very complicated. So, make things simple as you can. And what is the simplest possibility? It is the flow over a flat plate. Okay, so the flow over a flat plate. And we've done it also in white. We've looked at coheed flow. Okay, and then we went back into the continuity equation and the momentum equation, and you've derived the velocity distribution for certain boundary conditions. Okay, now that's a very simple case. Now let's look at the flat plate like this, where now we have a free stream velocity, but also a certain temperature, and obviously this plate is at the temperature Ts, and our coordinate system we put there, x and y. Okay. And then they wanted to look at the velocity distribution and the temperature distribution over a flat plate, the heat transfer over it. Okay. Now this case is more complicated than coheed flow, because we also have a velocity in the y direction, because this is just a boundary layer developing here of a very thick flow over it. And then the result is that if you go and look at your three equations, firstly the continuity equation, then it's going to look exactly the same as for coheed flow. Partial du dx plus partial dv dy is equal to 0. Okay. So that is coming out of the continuity equation. Then for the momentum equation, it would be equal to u multiplied by partial du dx plus v partial du dy is equal to the kinematic viscosity multiplied by partial d2u dy squared. Okay. Remember, can't throw out the viscosity now because they want to get things like the drag. Okay. Okay. And then the third equation is the energy equation, and the energy equation would be u multiplied by partial dt dx plus v multiplied by partial dt dy is equal to alpha multiplied by partial d2 d2t dy squared. Okay. The question is, solve it for me, please. Okay. Now that was Prandtl. Prandtl was a professor, as I've said, in the late 1800s. And that is the problem he gave to his student Blasius. Okay. Blasius had to solve this problem for him. Get an analytical solution for this equation. Okay. Obviously, there are boundary conditions. Just go and look at it. There are boundary conditions, as we know, that the velocity should be 0 on the plate, etc. So that is known. And the problem that poor Blasius had is he had to solve these equations. Okay. Now, what he did is, Blasius, in 1908, I don't know how, but also through measurements, looking at the results, he came out with defining this similarity variable eta, which is equal to y multiplied by the velocity v divided by the kinematic viscosity divided by x. Okay. And with this similarity variable, it was possible for him to firstly do the first two equations and to change them from two partial differential equations to one ordinary differential equation. So we took the first two equations using the similarity variable, changing them to one ordinary differential equation, and also using the stream function approach. You'll remember that we did the stream function where we said that the velocity is equal to, where's that thing now, partial dψ dy, and v is equal to minus partial dψ dx. What is the psi? It is sort of the path a flow molecule would follow. That is the stream function. So we use this similarity variable, those two things, and I'm going to spare you all the mathematics. We're not going to do that in detail. Okay. And the result was that he then developed a third order differential equation looking like this. Okay. So he figured out how to do that where f is a function of eta, and that is equal to the stream function divided by the velocity divided by the kinematic viscosity multiplied by x divided by v. And what he did is he solved this problem using a power series expansion. Okay. These days we will solve it numerically with a third order Runge-Kutta, typically. So you can go and do that. And then he managed to get eta as a function of f and other things. But that we will discuss with the next lecture. Thank you.